Good morning, dear participants. I welcome Dr. C. Sharada Prabhakar Madam, Scientist G, retired Scientist G, former Director, Advanced Composite Center, Advanced System Laboratory. She is presently DRDO Fellow, DRDL. She is delivering a talk on processing of composites. I request Sri Vidya to give a brief introduction about Madam.
Hello, ma'am. Good morning. Can you hear me, ma'am?
Now we can hear you.
Okay. Good morning, one and all. I consider it a great esteem to invite Madam Dr. Sharada Prabhakar Chavali, Scientist G, retired former Director of Advanced Composite Center, Advanced System Laboratory, DRDO, Hyderabad, presently DRDO Fellow, DRDL, Hyderabad. She is specialized in advanced polymeric thermoset composite products for missile applications. One of our greatest achievements is developing Caniston technology for missile applications. Ma'am has many publications in national and international journals. She was also honored by many awards and recognitions, and also delivered many technical and non-technical talks and also organized programs as technical session chairperson, member panel discussion in international and national conferences. We are extremely delightful to invite and have your sessions, ma'am. Welcome, madam. It's over to you.
Thank you. Thank you very much. Good morning to all of you. Shall I start, madam, lecture?
Good morning, madam. You can start, madam.
Okay, thank you. So today I'll have talk on processing of composites by in this AICT Atal FDP program, which is conducted by OU Mechanical Department, and title is Novel Materials. So I think on the appropriate topic I have chosen, processing of composites. It's a very novel material if you process it properly. So I'll just start the presentation. I'll be covering these areas: composites, what is composite, main constituent of composites, classification of composites, PMC, MMC, CMC, and CC composite. That is polymeric matrix composites, metal matrix composites, ceramic matrix composites, and carbon-carbon composites, and advanced composites. Little bit about. Then processing of composites. In that main, actually material characterization, it is unlike metal. Metal means isotropic properties, just we'll characterize. But here it is elaborate material characterization has to be carried out before even design of any composite product. So I will be covering mechanical characterization, then processing methods of composites, and at last metal composite joints also little bit I'll take up, because alone composites we cannot work with. It's a huge big structure. If we have to make, we have to join with either composite or composite metal. So little about metal composite joints also I'll be talking. What is composite? Composites actually two or more materials combined on a macroscopic scale and to form a useful third material. Constituent materials here we can see with naked eyes. That is the difference between alloy and the composite. Alloy means in microscopic scale we'll add different materials combined on a macroscopic scale, and after alloying we cannot see the constituent materials. Okay, properties we may be getting. And these composites exhibit best qualities. Sometimes properties of the composite which we made with constituent materials may be better than individual composite constituents. So that is why it's the composites. And why composites to use? Composites, if you see, it is a high specific strength and high specific stiffness. Specific strength, when I say it is strength by density, means whatever strength we achieve, it is a very low density composite material. So in turn, I can say it is very light material. That is why we use in aerospace and defense applications very high use of composites. Of course, automobile also many composite components are there. And here, tailored directional properties we can achieve. Whatever direction we want more properties, we can get fibers in that direction so that we can get better properties there. And it will be ease of fabrication. Ease of fabrication means many methods are there, fabrication methods. So we can easily get, and number of products will be, number of components we can get more. and complex shapes and special contours also can be made. And because layered structure it is, so it is a redundant load paths and better dimensional control for thin and long sections, and inherent damping characteristics because it is a layered structure. So damping also it will be better, and better fatigue properties because of layered structure. And it is a versatility, variety of fibers and resins. With that combination, we can have composites. And it is a high corrosion resistance. Once I say corrosion, there is no question of corrosion in composites, but some composites absorb moisture. That is why and they degrade, integrity will go. That is how we can say corrosion thing. But otherwise, it is corrosion resistance and better NHV properties. That is noise, vibration, and hardness characteristics. So here in composites, when we deal with to create a material to some specified function. Once I say specified function means whatever component we are doing, that it has to be loaded. So that direction put the fibers and put very less fiber, so that all the strength will be in direction required. So specified function, it has to function.
Madam, sorry for
main constituents of composite. Thank you.
Just some break in your voice, madam. Just check audio, madam.
Hello. Hello.
Hello. Now clear, madam.
Voice clear. Okay. So clear. Main constituents of composites are reinforcement and matrix material. These two are main. Other we can fillers and other additives also to improve the properties. Main constituents are material. Reinforcement basically and our fibers the load. Almost 70 to 90% of the load is carried by fibers, and it will provide stiffness, strength, thermal stability, and other structural properties in the composites, and sometimes electrical conductivity. Fiber use. If we use insulating fiber like glass, thermal properties will be insulating properties. If we use carbon, slightly conductive properties we get. So electrical conductivity and insulation. Function binds the fiber together. It is used to the
Please don't mind, madam. Sorry for interruption. Voice is breaking, madam. Just check audio, madam. Just once. Please don't mind.
Okay, ma'am. Okay.
Okay, madam. Okay.
In between, voice is getting broken, is it?
Okay. Little bit. It is happening.
Oh, okay. Maybe it's coming out or something.
No, ma'am.
Okay. Many gadgets are there hereby. Maybe that is the reason.
Okay.
Okay, madam. Sorry for disturbance.
Sorry for. Thank you.
So, main functions of matrix materials are it binds the fiber together. As I told, all the fibers will be bonded together with resin, and it transfers the load to the fibers. Without resin, no load transfer because fibers will be distributed. And this resin provides the rigidity and shape to the structure. If you don't add resin, it will be flexible like our cloth and fabric. Once you add resin, polymerize it. If it is a polymer composite, if it is a metal, you heat treatment it. If it is ceramic, if you sinter it, then you will get the rigidity and shape to the structure. Ductility and impact strength of the composite maximum depends on the matrix material, and failure mode also strongly depends on this material. And it provides protection to reinforcing fibers. Means once it is with resin, bonded with resin, and it will provide chemical attack and mechanical damage resistance against those things, and provides the good surface finish quality once we add resin. Classification of composites. Classification of composites based on construction and based on matrix material what we use. So based on construction, it is a fibrous composites. They are long fibers in a matrix. Laminated composites is a layers of various materials we stack one over the other. That is called laminated composites. Particulate composites. When particles of reinforcement we mix in matrix material, it is called particulate composites. Random composites, it is a fibers randomly distributed and oriented in the matrix material. And flake composite. Flake, sometimes reinforcement is in the form of small flakes that will be used in matrix material. So that is called flake composites. And if you see the matrix based on matrix material, it is composite is classified as polymeric matrix composites, where polymer material or polymers are used as matrix material, basically resins. Metal matrix composites, metal fibers are also metal, and matrix material is also molten metal. And the ceramic matrix composites, ceramic is the matrix material and fibers are ceramic. And carbon-carbon composites, it is a carbon matrix reinforced with carbon fibers. So ceramic matrix and carbon-carbon composites are used for very high temperature and ultra high temperature wherever applications. Metal matrix composites we can use up to 500 degrees centigrade, and polymeric matrix composites up to 400 degrees centigrade. And lot of polymeric matrix composites are general use in aerospace and defense application, even automobile application, marine environment. Many polymeric composites are used because of lightweight. Types of reinforcements, general use is fiberglass, which is e-glass. That electrical purposes it was invented, but now many applications are there for e-glass, which is very cheap, and general composite products we make with fiberglass composites, fiberglass. C-glass is a corrosion resistance, R-glass high strength corrosion resistance, S-glass again high strength, D-glass dielectric properties are very good. So aircraft radomes and are made with D-glass. Then carbon fiber, graphite fiber. Carbon fiber and graphite fiber are very high strength. For carbon fibers, base material is a PAN, that is polyacrylic nitrile, which will give very high strength, high modulus materials we can use. Graphite fibers we can use, and aramid fibers. This is dew point. It is called as a Kevlar fibers. The various grades here also based on stiffness. The grades are available: Kevlar 29, Kevlar 49, like that. Then silica fibers. And the boron fibers we get, silicon carbide fibers we get, and silicon carbon fibers we get. And polymer matrix material, based on matrix material, the polymeric matrix materials are polyester, general use. Whatever we say, we see that many components in our daily use are made with polyester. Of course, it is health hazardous, but general components are made with polyester. Vinyl esters, then epoxies for electrical insulation purposes, many purposes it's used, and for structural composites. And phenolic resin, whenever these components are required at 400 degree, phenolic, polyamide, bismaleimide, all those high temperature resins we use. Then cyanide ester also is a very good material for electrical, dielectric use. Very low dielectric constant is there with cyanide ester resin. So these are the matrix materials in general we use. Then metal matrix materials, aluminum alloy, aluminum and its alloys we can use, titanium, magnesium, copper, then nickel-based superalloys, and stainless steel we can use. These are the metal matrix materials we generally use. Types of ceramic matrix, aluminum oxide, carbon, silicon carbide, silica, and these are all materials. Ceramics composite materials are very highly useful for very high temperature applications. Otherwise, they are fracture toughness is very low. So only high temperature, it retains the strength. So that is the best use of ceramic matrix composites. Fibrous composite, as I told you, based on construction, fibrous composite means fibers in a binder or matrix material or resin. Basically, polymer means it is a resin. And fibers are, as I already told you, fibers are principal load carrying members and provide necessary strength and stiffness. And resin supports the fibers, give shapes to the fiber, and acts as media for load transfer. Fibers have actually very low size, crystal size diameter, 5 to 10 microns. Lower the size, fewer the internal defects, better the properties compared to bulk, and more perfect structure we get. Better properties, suppose if you see ordinary glass plate, fracture toughness is very low, 20 MPa. Once you draw the fibers, glass fibers, almost strength in fiber direction we can get, fiber strength we can get from 2800 to 4800 MPa. That is as glass, R glass, very high strength, 4800 MPa, up to that we get, because it's a very high L by D ratio. So we get very good properties, very high properties of fibers compared to bulk form. Resins have, and resin, it is mixed with fiber. So resin has very low density and lower strength than the fibers. In this figure, you can see These are carbon fibers and matrix materials. These are CFRP structure, it is called carbon fiber reinforced plastics. See, only fibers, there is no use. Once you bond it with resin, then only take the form of structural element that can carry the loads. And the combination of fibers and matrix material gives properties with lower density, higher properties, sometimes properties better than constituent materials alone. Laminated properties, laminated composites. Lamina consists of fibers placed in a matrix material. It is called lamina. It is a building block. So more than one or two or more than two laminas, they are bonded together. That is called, it is laminate. Means lamina are stacked together and it is called laminated composites. The lamina is the building block of a laminate. Bimetals, if you see, thermostats are there, clad metals, that is sheathing of one metal with another metal. And laminated glass. So these are all laminated composites because the laminas are stacked together to form a laminate. Particulate composites. As I told, particulate composites means particles in a matrix. Matrix can be non-metallic particles in non-metallic matrix. Just example, one example I have given, many are there. Non-metallic particles in non-metallic matrix, that is concrete. Metallic particles in non-metallic materials, that is solid propellant, solid rocket propellant. Metallic particles, alumina we add in elastomeric, generally composite propellant. And metallic particles in metallic materials, that is lead particles, sometimes we add in steel to improve the machinability. Particles in metallic matrix, metallics is ceramic in metal matrix, that is cermets we use as many places. Particulate composites are quasi-homogeneous and quasi-isotropic. In general, composites are heterogeneous, not homogeneous. Heterogeneous means the properties are depend on the direction or orientation at a given point. Random fiber composites. Random fiber composites, the fibers randomly oriented in a matrix. Small fibers are randomly, it is mixed with resin. So randomly they are oriented. So for design purposes, analysis purposes, we can take this property isotropic. Flake composites, they are flakes in a material. Mica flakes, you can see it is in materials used. Flake material composite, many places it is used.
Madam, screen. Padmala Madam.
Sir, I am here.
Screen almost disappeared. Madam's presentation.
Yes, sir. Saraswati Madam is checking. Just 1 minute. Now visible, Madam.
Yes. Yes. Now it's okay.
Presentation.
Madam, voice in Bisle.
I think they are checking, sir. Just.
Is it okay, ma'am? Naturally occurred composites.
Yes.
Yes, madam. We can see the screen clearly. We can see. Voice is also clear, madam.
Naturally occurred composites are wood. Wood, if you see, this is the reinforcement is cellulose fibers and matrix material is the lignin. Then bones are also composite materials. Reinforcement is bone salt plates made of calcium and phosphate ions, and matrix material is a soft collagen. So many composites are there actually naturally composites in our body itself. Natural fiber composites are asbestos phenolic, jute fiber composites, and sisal fiber composites. They are all natural fibers. Asbestos, jute, and sisal are natural fibers, and man-made fibers generally we use for high properties. These are the mechanical properties. Actually, a specific strength and specific stiffness is more. If you see carbon fiber, specific strength almost it comes in 2000, 3000 and all, whereas metal, it is less than 100. So that is how it's the specific strength and specific stiffness is more for composite materials. I just put this transparency to show that. If you see steel, aluminum alloy and titanium alloy, it is slightly hundreds. And that carbon fiber, it will be, if you see strength by density, it will be hundreds. So that range is the increase in properties. Hello.
We can hear you, madam.
Okay. Many places we call it as advanced composites. Composites are general, made with reinforcement and matrix material. Advanced composites, traditionally they are used in aerospace and defense applications. High performance reinforcement, if we see pan carbon, high strength carbon. General composites, general use composites, we make with e-glass and very cheap. And advanced composites generally we make with pan carbon, high strength carbon fiber, high modulus carbon fiber. Base material is a polyacrylic nitrile. And graphite fibers, Kevlar fibers, boron, tungsten, aluminum, alumina, silicon carbide. These are metal and ceramic fibers. Silicon nitride and silica. These are the fibers when we make with composites. They will be used in defense and aerospace applications, and they're called advanced composites. Matrix materials are polymeric matrix materials, epoxy, phenolic, polyamide. They are high temperatures. Cyanide esters for electrical purposes. And metal matrix materials are there, and ceramic matrix materials, many matrix materials are there. SiC, carbon, which we use as matrix material for advanced composites. Because reinforcement, as already I told you, advanced composites are thin diameters, so very minimum internal flaws, and that is how properties increased. Better load transfer from matrix to fibers for the same volume fraction because surface area is increased, and better flexibility required for woven fabric. So as diameter reduces, weaving will be very better and flexible because rovings are flexible, so we can weave fabric easily and flexibility. Advanced composites can be PMC, polymeric matrix composites, metal matrix composites, ceramic matrix composites, and carbon-carbon composites. Carbon epoxy composites, if you see the aircraft structure, many structural products we use in aircraft, like aircraft control surfaces, wing, fin, and stabilizers. Then many airframe sections we use, engine parts we use. And there are many are in different applications. Then Kevlar epoxy composites, their impact strength is very, very high compared to other composites. So many applications are there. Boron aluminum, silica composites we use. Silica composites for better insulation. SiC, that is silicon carbide we use. Because very low erosion, means mechanical erosion will be very, very low. So jet vanes we use. And carbon composites we use in defense application for brake disc and nose cone of the re-entry vehicle. These are the various forms of composites. Various forms of reinforcement. Will have various forms. Glass is glass chemical resistance. Glass, as I told you, electrical insulation. C is a chemical resistance. S glass is the highest tensile strength is offers. D glass is a low dielectric strength. R is the various forms of fibers are available. It is rovings. Roving is direct collection from continuous strands from the nozzle when we make the fibers and spinning. So directly from their nozzles we collect the fibers. That is called roving, and it is always measured in tons. That is the weight of 1 kilometer. 1 kilometer. Small strap into 1 to 2 inches and you see panel stand.
Madam, sorry for interruption. Sorry, madam. Voice is breaking. Dear participant, just wait 2 minutes. Madam will start her session.
Hello.
Hello, madam. We can hear you.
Okay. There was small disturbance here. Sorry for
No problem.
disturbance.
No problem.
Unstable. Fiberglass mat. It is a choke. It can be made with choke stand mat, 1 or 2 inches length. This was even it will be cut and evenly distributed at random onto horizontal plane, and chemical sizing is applied. That is in our coolers and all. We can see last layer. It is a choke stand mat. Then continuous stand mat also will be there, made of continuous stands of fiberglass deposited and interlocked in a spiral fashion. That layer also we can see in our cooler plates. It is a last layer. This mat is open and flexible, but due to its mechanical interlocking, it does not require any chemical sizing or binder. So that's how these are the stand mats, and even carbon also will be there, stand mats. Then textile fiberglass yarn. Yarn, when we weave the fibers, so for weaving, actually directly rovings, if weaving, like rowan weaving, it will be very coarse and all the fibers will be not put together. So little twist if we apply. So that is called, yarn is called when we apply twist to the rovings in the form of textile. So when we, for weaving, this is additional strand integrity has to be added by twisting the yarn slightly. Less than 1 ton per inch if we twist the roving, it will be yarn. It will be called yarn. And for all our even clothes weaving also, we make first yarn. That is why it's called yarn. Then milled fibers. These are milled means almost 2 to 6 centimeter hammer milled into very short fiber lengths. That is 2 to 6 mm. These are added as a filler materials in the composites. These milled fibers. And surface mat. It is fine wool mat. It will be there. Like in our ovens, if you see, fine glass wool will be kept as insulation in insulation panels. And various fiberglass views are there, like plain view, what we wear the clothes, one warp and one warp over and under the fill. And basket view, twill view, then 8H satin view. Satin view means it will be like our satin fabric, very flexible. So one yarn will be in warp direction and it is in an irregular fashion. It will be very high strength and very, it conforms to the mold. That is why generally we use 8S satin view in our all fabrics. Then unidirectional fabric, as I told you, all the fibers in warp direction. So there we'll get very high strength, and other direction just we have to bond the fiber with some polymer fibers. So various views are there. Then coming to processing of composites. Basically, 4 items are required for processing of any of the composite product. Unlike metals, we start from raw materials like sheets, forgings, bar stock, anything, or casting. If it is a cast structure, it is casting. All composites are made on a tool. So tool is must here, and raw materials and heat and pressure. because you have to either heat treat if it is metal matrix composite, polymerize if it is polymer matrix composites, and sinter it is if it is ceramic matrix composite. So heat and pressure are making, and many indirect raw materials are used during processing, like mold release material. So all polymers and metal matrix ceramics we are depositing on the mold. So it has to be get easily released from the mold. So many mold release materials we use, generally they are in the form of fabric, film, and liquids. Lot of polyvinyl alcohols, PVA, if you see, for polymeric matrix we use as a PVA as a release agent. That release agent will be having affinity to the composite and not very affinity to the mold, that is metallic molds. And bagging materials, sealant and sealing bags we use, because as I told you, heat and pressure is applied, sometimes vacuum, because a lot of volatiles will be generated during polymerization of the polymer composites. So for taking out extracting the volatiles and again applying pressure, we want vacuum bagging materials, vacuum bag. So vacuum bagging materials are required, and those bag has to be sealed properly. So a lot of sealants are required, and other consumables also, many consumables are required. So polymeric matrix composite making, processing of polymeric matrix composite is like cooking. Cooking may many materials are required apart from raw materials, direct raw materials. Apart from that, many materials are required. Same way, processing of composites also requires many materials. So we call it as a direct raw material, indirect raw material. Then there are 4 basic stages in the processing of composites. First is the impregnation. Impregnation means fiber and resin are mixed together to form a lamina. And in this, during impregnation time, we have to make sure that resin flows entirely around all the fibers. So these are the parameters which affect the impregnation process, is the viscosity and the capillary action. We have to choose resin and fiber in such a way that resin is getting wet. Total fiber is resin getting wet with resin. This in impregnation stage we have to see. Automatic impregnation also we can do, manual impregnation also we can. After impregnation, it is a layup. As I told you, composite materials are layered structures. So we have to lay up the composite based on design, means in what orientation and what direction we have to put our reinforcement or layers. That is pre-decided in the design stage. Accordingly, we have to do the layup. Like if I want in shear properties, so plus minus 45, I'll put. I want in unidirectional properties, so all fibers are in unidirectional, all layers are in one direction, we put. Like that, many as per design, as per requirement, at desired angles, and we place the composite laminas. So that is called layup, and there they are needed. And it is a fiber, it depends on fiber architecture by design. Designers will give at what angle you have to put the fibers. Then fiber orientation and the layup sequence. Sequence also, how sequencing we have to do, hoop layer top may, or helical layer in between, or fiber mat, or matrix mat, or fabric layer. That's how layup sequence will be pre-decided. So then we have to do the layup. So impregnation, layup, consolidation. As I told you, layer by layer we are depositing, so a lot of air pockets will be there. Air will be locked inside, in between the layers. So that air you have to remove. Then resin flow we have to make sure, and elastic fiber deformation. So for all these things, means carefully we have to consolidate. So many automatic processes are consolidation. What we generally use for air is by layers. So all air, water, everything will get removed and consolidated. Solidification. So after impregnation, layer, consolidation, then you have to solidify. Solidify means it is like curing. Like cement, we cure it. Same way, polymeric matrix composites, metal matrix composite, and ceramic matrix composite. All composites we have to solidify. So they will be under vacuum, pressure, and temperature. There are 4 steps of composite product fabrication. First is the forming. This is general for any of the composite. Forming, like other methods I told you, impregnation, layup, consolidation, and solidification. After that, you will get as a feedstock. It is changed to desired shape and size. So already we have got by earlier 4 processes. And once it is ready, that material, now we have to machine to the size to remove extra materials. Near net shape we make by forming, and then to actual dimensions, we will machine it. Then it has to be joined. So joinery, for joinery, if it is a preparation, if it is molded joint, drilling, cutting composites, there are different tools required for machining of the composite. Basically, carbide tools or PCD tools we use for composites, and operating conditions also are different. Then third step is the joining and assembly. So joining of composite to composite to metal, and they are bonded joints. They can be bolted joints and bonded and bolted joints. Then last is the finishing operation. Finishing operation, like any other metal, we have to improve the outside appearance and to protect the product against environmental degradation, and wear resistance coatings we can give. And sometimes composites are made and metal coating is given that resembles that of the metal. So these finishing operations are also required. So they are the 4 stages of product fabrication. The processing of composites. These composites are of two types, thermoplastics and thermoset. Thermoplastic composites, when we apply the heat, it will again change its shape. That's a thermoplastic. All our general use items, right from morning, if you see brush to toothbrush, our bucket, mugs, all these things are thermoplastic, made of thermoplastics. Once you heat it, they'll change the shape. Again, you can remake the composites. Whereas thermosets, once you heat and polymerize, they cannot be reshaped. Rather, it cannot be melted. They'll directly char. So they are the thermosets, which will give better properties, high mechanical, thermal, physical properties compared to thermoplastics, but they cannot be recycled. And it can be, these are the thermosets. Thermosets composite processing is continuous fiber composite processing and short fiber composite processing. Thermoplastics also continuous fiber composite processing and short fiber composite processing. Continuous fiber composite processing, I will be taking only thermosets because of time limitation, because many methods are in there in thermoplastics also. Thermoset composite processing is like filament winding, pultrusion, resin transfer molding, hand layup, bulk material compound process molding and spray molding. Molding product may our general use, lot of electric plugs, switch panels, so are molded, short molded composites. Thermoplastics also, as I told you, continuous fiber composite, molding, autoclave, diaphragm mold forming. These are and short fiber composite injection and blow molding. Product development, I'll be taking now. These are general, I'm telling, general raw materials for manufacturing of polymeric composites. They are the reinforcement in the form of rovings, fabric. We use in the form of roving and fabric. Rovings are E-glass, R-glass, S2-glass, pan carbon, that is nitrile, carbon fiber, T300. They are graded as T300, 700, 800. These are the filaments and high modulus carbon fiber, Kevlar. And same fabric we can use with this E-glass, S2-glass, pan carbon, silica fabric, rayon-based carbon fabrics. And resins we use as a epoxy resin, phenolic resin, cyanide ester, low loss polyester for electrical purposes, cyanide ester for electrical purposes, polymer and silicon resins. Prepregs also we can use. Prepregs are nothing but resin and fiber. We mix, pre-mix beforehand. That is called toe preg. If you do use rovings, it is called toe preg. If it is, and fabric prepreg also we can make. So here controlled quantity of resin will be there, and it will be staging, little bit advanced stage of polymerization. So that's why we will get the neat component, sound component, and properties are good. So toe pregs, we can use pan carbon. Now in our country, it is available pan carbon toe pregs people are making. E-glass, S2 glass, R glass, epoxy, then benzoyl resin. These are the toe pregs are available in the country right now. Fabric prepregs again, E-glass, S2 glass, E-glass phenolic, silica phenolic. With epoxy resin and phenolic resins, we are making a lot of prepregs, fabric prepregs are available in the country. Then we use a lot of elastomers like nitrile, silicon, white-on rubber for seals, nitrile rubber and EPDM for casing insulations. Wherever insulations for high temperature application we use as a lining materials. Then a lot of sealants we use. These are the raw materials. Some pictures I have given. Raw materials used for manufacturing of polymeric products. This is the high silica fabric. Then it is not very clear. It is a carbon rayon-based carbon fabric. Rayon-based. Once I say rayon-based carbon fabric means rayon yarns are woven into fabric, and that fabric is carbonized, which is used for high temperature applications. Pan carbon fabric is used for high strength applications, and rayon carbon is used for high temperature applications. It does not have much strength, but high thermal properties are better. And we use phenolic resin. This is the rayon carbon fabric phenolic prepreg. And this is a glass filled phenol formaldehyde molding powder. As I told you, molding, a lot of molding processes are there. So already we make the compound, molding compound, which is used for molding of the components. This is the glass toe prepreg. As I told you, material characterization is very, very important before making any composite product. Unlike metals means isotropic properties. In one direction, just UTM test karne se this will go over. But here, in many directions, we have to find out the properties, and we have to characterize in detail mechanical, physical, thermal, and chemical properties. So for characterization of mechanical properties, we have to make unidirectional and bidirectional laminates. Unidirectional laminates are made with roving, and bidirectional laminates, I'm calling bidirectional means two directions, laminates are made with fabric. And mechanical properties, tensile strength and modulus in longitudinal direction, tensile strength and modulus in transverse direction. Same way, compressive strength and modulus in longitudinal and transverse direction, Poisson's ratio, flexural strength and modulus, interlaminar shear strength, and in-plane shear strength. Of course, flexural strength and modulus, interlaminar shear strength, these two are we call it as a workshop properties, because these they don't go in as design input. But these are basically resin-based properties. So how the resin, when it is mixed with fiber, how it acts. So flexural strength and interlaminar shear strength we use just before fabrication of the composite, and all other things are tensile, compressive in longitudinal and transverse direction, Poisson's ratio, and interlaminar shear strength. These are input for designing of composites. As I told you, the mechanical, then physical properties, resin content and density we measure on samples. Resin content, if we measure directly by weight, it will give the volume fraction of the composite, because generally we consider as a 60% volume fraction, means fibers are by volume, it is 60% in a composite. So we generally find out resin content and density. Then electrical properties, dielectric constant, and many other properties are there. Electrical resistance, because it should not be too high resistance. Some conductive coatings we give otherwise for use. Then thermal properties, thermal conductivity, thermal diffusivity, specific heat, and alpha. Alpha is important because accordingly tool material has to be chosen. Characterization of polymeric matrix composites. As I told you, fabrication of UD and BD laminates, thin laminates we use, and samples we prepare as per HTM standards and other standards and test. And these properties are the input for design. UD laminates are made by winding technique. As I told you, I think I'm not able to mark this. This is the UD. This is the UD laminate. This, if you see this plate is held between centers of the filament winding machine. This is tailstock, headstock. Between centers it is held with adapters, and this plate will rotate about its axis, and then we can deposit the fibers. So in one winding, we will get 2 laminates. So in one winding, you can see this unidirectional, this is schematic. We'll deposit the fibers in this direction, held the plate. After winding both sides of the plate, this is the winding. This is the winding, and then it will be kept in the mold top and bottom plate. Then it will be cured in hydraulic press under heat and pressure. That was the schematic, and this is actual. Extreme left is the unidirectional fiber winding, filament winding of carbon epoxy UD laminate. This is the glass epoxy UD laminate. As I told you, between centers plate is held and it is wound. This is the laminate I got from this after curing. This is the laminate we got from this winding. This is the bidirectional fabric laminate of glass. And for bidirectional, it is just die plate with spaces, and then we put the required number of layers and punch plate is put. That is how bidirectional laminates are made. This is rayon carbon phenolic bidirectional laminate used for thermal characterization. So this is how material characterization carried out by making UD and BD laminates. A lot of ASTM standards are there to perform these tests, and that we get the properties. Those properties we input for our mechanical and thermal design. Then physical properties we see to see the soundness of the composite, like volume fraction and density of the composite we measure. These are some of the pictures of. I'm not able to take the cursor, it's becoming very difficult. So just you can see, these are the tabs, first figure. Then adjacent to that is the carbon longitudinal tensile tested carbon epoxy UD sample. Beneath is the glass sample. Then here flexural test bidirectional samples are there. Carbon epoxy, tensile tested carbon epoxy BD sample, and flexural test failed sample of carbon phenolic BD laminate and glass laminate. So this is how is the material characterization is carried out. Of course, it is a very detailed program. Before manufacturing of any composite or aircraft composites, we have to do elaborate number of specimens we have to test. Here we are taking some 25 to 30 samples we take for each property. Whereas in aircraft, if you see the design on the allowables, so thousands of samples have to be done to get the reliable structure. Now coming to product, is it time there? Filament winding is the main process. With filament winding technology, we can get cylindrical components, long cylindrical components. Then we can get conical components easily, and even not only symmetric, unsymmetric components also we can wind. So filament winding technique. In filament winding, this resin impregnated fibers are wound over rotating mandrel at desired angle. I'm not able to take the cursor, otherwise I could have shown in the figure. Rowing from creel stand, it comes dipped in resin bath, come through carriage, and they are depositing on the rotating mandrel. So that is how is the filament winding. And filament winding, there are 3 types of filament winding. Helical winding, hoop winding, and polar winding. In helical winding, resin impregnated fibers are wound over rotating mandrel at desired helix, in the form of helix. You can see here, it is in the form of helix, fibers are deposited. For helical winding, this is the mandrel, tailstock, headstock, in between centers, filament, that mandrel is loaded. and with end domes. I am calling it as end domes because end domes are required for reversal of the fiber. In helix form, it will come, take the reverse, and then again it will come this form, then take the reverse and this. So end domes for any mandrel are used for fiber reversal. They are not the composite, they are not the part of component. In fact, without dome also we can wind. There we have to put the pins, and pins will be used to reverse the fibers, and then we have to remove the pins. This is the helical winding pattern. You can see forward, and this is the reverse. So one diamond-like thing you can see. And these are called the crossover points, wherever fiber is crossing, forward and backward fiber, they are crossing. This is the helical winding. You can see here helical winding with the dry rovings, forward and reverse. Then I told hoop winding. In hoop winding means this is the mandrel. Hoop winding means resin impregnated fibers are wound on a rotating mandrel at 90 degrees to the axis. This is the machine axis. If you see, this is the machine axis, and perpendicular to that machine axis, fibers are deposited. That is called hoop winding. From the creel stand, fibers are coming and they are getting deposited on the mandrel in 90-degree direction. That is called hoop winding. In this figure, if you see, these are the hoop winding. This is the helical winding. Then comes the polar winding. Polar winding is pole to pole. From this pole to this pole, we have to take the carriage, then take reversal.
Madam, sorry for the disturbance, madam. It is participants. Okay. I have muted, madam. Okay. Please continue, madam.
Okay.
You continue.
So in polar winding is carried out pole to pole on the mandrel. Fiber passes tangentially to the pole opening at opposite end of mandrel. From here it starts and get deposited opposite end of mandrel, then reverses, and again it is in the direction and passes tangentially to the opposite end pole. Then it will be indexed. So that is how pole to pole winding is done. It is a planar winding. So for very low angle of winding, like 0 to 5 degree angle, helical winding is very difficult. Lot of slippage will come. So that's why we go for polar winding. Like lot of bottles, if you see gas bottles, CNG bottles, they are generally wound with polar winding. Very low angle of winding. It is a special case of helical winding, basically. Then there are two methods, as I told you, toe preg winding and wet winding. In wet winding, of course, unfortunately, I'm not able to show you the resin bath because backside of the machine they are there. So in wet winding, dry fibers passes through resin bath and get impregnated and then wound on the mandrel. Whereas in pre-preg winding, already pre-impregnated toe preg means it is in the toe preg will be deposited directly on the mandrel. So here in toe preg, if we use, we'll get the good properties, good resin content. So resin content, required volume fraction we get, density will be good, sound component without much defects we get. So compared to wet winding, pre-preg winding is better. So generally in our aerospace and defense applications, we generally use pre-preg winding, but it is very costly because they are the shelf life based items. Once you impregnate with, once you keep resin and fiber separately, life is high. Fiber life, of course, in years, resin life also will be in years. Once you impregnate fiber with resin, hardly 9 months, 10 months only will be that too we have to store at minus 14 degree, minus 8 up to minus 18 degree temperature. Then only shelf life will be 1 year. So it is a costly affair, but very good quality component you get. So aerospace quality component to get, we use generally pre-pregs. These are the various methods. General any composite I'm telling. Winding for filament winding process, I've taken the example. So winding we have to do either helical hoop and a combination of helical hoop, and curing. Once we wind, we have to polymerize. So curing of filament wound section, it is already on the mandrel. So we will not really, we cannot release the component at that stage. With the mandrel, we have to put it in oven or for heat treatment, rather for curing. Either it is autoclave or oven as per specified cure cycle. Once it is cured, it will be hard. Then we can check the hardness. That further operations we have to carry out on that, like end domes parting are required for helical winding for fiber reversal. So those end domes we have to part it out. Then OD requires us, you have to machine, because what happens is in filament winding, constant volume of material deposition. So if your cross-section diameter is less, more volume, more thickness will be deposited. If your diameter is more, less volume, less material will be deposited. So here, basically, it is a near net shape component we get. So we have to little bit machine. Of course, machining in composite is not advisable because we lose mechanical properties. So generally, composite will be designed by degrading 10% of mechanical properties to cater for machining operation, because near net shape only we can make. Then once we machine it, then extract the machined component from the mandrel by either pulling or pushing the mandrel with axial force. So then only component can be extracted from the mandrel. Then of course, finish coat as per requirement, as per aesthetic we can give. Then non-destructive testings we have to perform, either X-ray or ultrasonic, and dimensional inspection is very much required. And then joineries, if it is a bonded joint, surface preparation; if it is a bolted joint, drilling of holes to the joinery surfaces. So this is the general process. That was the filament winding. This is now pultrusion. Pultrusion is a continuous process for manufacturing of fiber reinforced plastics with constant cross section, like I section, C section. So constant cross section and more length. So in pultrusion, we can see fibers are coming with guided plate, getting impregnated in the resin. Then preformer, basically it is a die, extrusion die, pultrusion die. Then they will get cured here, and then constant cross section under pulling system, and then cut off. This is one more thing. Continuous fibers are coming in the guided plates, getting impregnated in the resin bath, heated die, then force, and then cutter. So these are the pultruded rods we are getting. Then autoclave, because it is open molded process. Then pre-preg layers are cut, laid down in the desired fiber orientation on the tool, and then it is followed by vacuum bag and putting in autoclave and curing under temperature, pressure, and vacuum. So here it is pre-preg hand layup we can do, tape layup we can do, and rosette layup we can do. Pre-preg hand layup is basically cylindrical sections. For making this down figure, it is making cylindrical sections. You cut the fibers, cut the fabric in a specified dimensions, and laid down on the surface of the mandrel, cylindrical mandrel. And number of layers you have to put to get the required thickness. Then make the bag, vacuum bag, put it in autoclave and get cured and machined. So this is the component we get. This type of component we get. This is the mold finish, and this is the OD we have to machine and get the thing. Then tape winding, fabric pre-preg tape winding, tape of 100 to 150 mm width laid down on a hoop direction at a specified pitch on the metallic conical mantle. This is followed by vacuum bagging. So here winding is made tape winding. Between centers, you have to load the mandrel, conical mandrel. Then in a hoop direction, we have to put the tapes. Hoop winding we do with roving, and tape layup we do with, it is also in hoop, but in tape, 100 to 150 mm tape we use. Then rosette layup, it is like laid down on the longitudinal direction on the conical mandrel at specified pitch. So conical mandrel smaller and bigger end circumferences are divided into 6 to 8 segments, and based on the thickness, number of layers which is decided, and pieces are cut with help of template. These you can see the number of layers are stacked in this plane. This is called, in Hindi, if I say, it is called tash ke patte. Just you arrange in tash ke patte like. So that is the, it's like rosette layer it is called. Because one end is always inside. So here high temperature performance will be better because one end is always locked. So erosion will be less. We call it as erosion, means take away the material under temperature. It will be less in this component. So generally convergence of nozzles, we use this process. Then this is the match die molding. In match die molding, die and punch, the male-female parts of the mold are matched with fasteners, and required number of layers are impregnated with resin and laid down on half the mold. Generally, this mold we make layup, and other half is matched to this and clamped, and which is followed by curing. So no vacuum bag and all is required for this, unlike autoclave process. So this is the picture. In this mold, that socks, we call it here as a socks, because reinforcement we will stitch in the form of socks. Socks are put one over the other and impregnated with resin. So this is match die molding parts we can make with this method. Then transmolding. This process is useful for production of cost-effective structural parts where both side finish is required and medium volume, not very high volume, medium volume. So there we use RTM. RTM literally it means resin transfer from one machine to preform. So in one mold, we make the preforms, stack it, resin is transferred from another system to this from the bottom through the nozzle under pressure. And from top, if require less time to get impregnated, from top we can apply vacuum and pull the resin against gravity. So this is how RTM is used. The resin is injected at the lower point of the mold and flows upwards. This is against the gravity to minimize the entrapped air. And our top side also we can apply vacuum. So that is the finished product we get. This process is used for very thin components, compression molding. This process is used for very thin and complicated shape components. And molding compound is starting material and mixing resin and reinforcement prior to molding, known as molding compound, or it is a dough or molding compound. See, this is the material it is kept in the heated die. This type of component we have to get. In heated die, this material is charged, and then from here it is pressed. So this type of component we get from the mold. In compression molding, very high pressure is applied here. That is why it's called compression molding. Compression molding is used when number of very high volume we have to make the products and close tolerances, and of course surface finish. Because both the sides we get surface finish here. One side, die side. Method quantity of molding compound is based to mold. Mold under pressure. Mold is closed under pressure. Molding compound will be it will flow under the heat and pressure and fills the mold and cures. This is the molded component, complicated shape. Very thin and complicated shape component is made by compression molding technique.
Dear participant, just wait, madam will join in 2 minutes.
Of this presentation, could you please ask her to circulate the same slides, or if not, some.
With madam permission, I will share in our group.
Please, madam, because it will be clear.
రాదనుకుంటా, షేరింగ్ లో రాదు కొన్నిసార్లు. ఓకే, ఏం కాదు, పెట్టేసి పెట్టేసి ఫైన్ మా ఇక్కడ యూజ్ దిస్.
ఓకే.
If you are comfortable, no problem.
So this was the compression molding component. Next, I'll take up. Those are the manufacturing methods I have taken: filament winding, pultrusion, compression molding, resin transfer molding, match die molding, etc. Autoclave process, and little bit about tools and molds for fabrication of composites. Type of tool depends on manufacturing technique. Filament winding requires mandrel. This is the mandrel. These are the end domes. End domes are fitted to this and carry out the filament winding. RTM, match die molding, requires closed molds. Then pre-preg hand layup, tape layup, and rosette layup require mandrels again. Pultrusion uses a die. Wet layup generally requires FRP molds. We make fiber reinforced composites molds also. And surface finish of the component depends on the surface finish of the tool. This surface finish actually we get for all our winding processes. It has to, first is the dimension. Little taper for extraction we give. This is over 8 meters length over this thing, and almost 1 meter diameter. So 2 mm on the diameter we give taper, extraction taper. Plus surface finish also we use almost N6 grade. So then only smooth surface of inside surface of the composite component we get. This is the die for compression molding. This is the compression molded component. This is the die. Design criteria is shrinkage allowances for composite material and mold material, both we have to take. And coefficient of thermal expansion of tool material and composite material end product should closely match to avoid the residual stresses and dimensional inaccuracies. Sometimes what happens, alpha, if it is different, mold extraction also will be very difficult. Because once it cools down, if alpha of the composite is more than metal, then it will hug the composite, hug the mandrel. So removal of composite from the mandrel will be very, very difficult. So these alpha we have to see. There should not be much mismatch. And during curing also a lot of residual stresses will be generated. The stiffness of the mold should be stiffness to take the processing pressures. Like in autoclave pressure, we are applying the pressure, it has to take those pressures. In filament winding also with tension, we wind the component like helical winding, and also it has to take those loads. So mold should be designed in a proper way. It has to take vacuum loads, it has to take pressure loads, it has to take winding loads, handing loads, those things. And surface finish quality, always mold should be one quality higher than the component. Suppose N6 I want component, so N5 or N4 mold finish has to be there. Then only N6 component I can get inside surface finish. Then of course proper draft and corner radius we have to give, avoid sharp corners. It's like as usual for metals. So that was all about fabrication of the composite. As I told, metal composite joints I will take up. So metal composites joint can be, see composite, sometimes what happens is because of facility limitation, very big components we cannot make with the machines. Even if we make the components, inspection would be very difficult because composite are highly process oriented. So a lot of NDT methods for checking the soundness of the composite we have to carry out. Non-destructive testing. So all the components in radiography we cannot take, or ultrasonic also it has to be approachable. That is why the size of the composite component making is restricted based on facilities, based on inspection methods used. So we have to join, for getting the big assembly, we have to join the composite components either another composite component or to metal component. So metal component joints, very critical design it is, because very high mismatch in EI we see in metal composite joints. So very carefully we have to design the joints also. And they are the weak link in the composite, in the assembly. So joints are bonded joints, bolted joints, bonded and bolted joints. And mechanical joints are very more efficient joints than bonded joints. And bonded joints can be overlap joint and axial joint. This you can see metal composite plate, it joined with two metallic plates on either side with axial joints. So what we have done is long hole is made on the face of the composite plate and on the face of the side face of the metallic plate, and long stud is put. Here nut is tightened, here one insert is there and stud is matched here. So that's how we get the axial joint. For seeing it looks to be very simple joint, but very complicated to realize because very deep hole we have to make in the composite laminates, that too again along the layers, along the thickness side layers we have to make. So a lot of delamination, drill drifting, all those problems we will face. So we have to carefully make the hole in composite. Same way, overlap joint, these two metallic plates are joined with this composite, single composite plate by radial joint. So this is the lap joint, radial joint. So here it is long holes we have to make, in situ holes in metal and composite. On cylindrical composites also we can join. So here we have to take care, we have to do in situ drilling on composite as well as metal. And always composite should be inside in lap joint and metal should be outside, because composite expands more than metal. Because of mismatch in EI, a lot of stresses will be induced. That's why inside we have to put the FRP and outside we have to put the metal. So this is the joint, in situ drilling we have made. These are all about joints. Now that what processes, tools, about molding methods I have explained about polymeric composites. I'll just quickly go through metal matrix composites and ceramic matrix composites. I'll not take much time because time is already over, I think. The processing of metal matrix composites can be in solid state processing, liquid state processing, and in situ processing. In solid state processing means both will be solid, matrix material and reinforcement. Powder blending and consolidation is one the method generally used for aluminum and magnesium MMCs composites for short or particulate composites, particulate reinforcement. And diffusion bonding we use for widely aluminum and magnesium MMCs when continuous fibers are there. Physical vapor deposition method also can be used. Powder blending consolidation for short fibers, diffusion bonding for continuous fibers. So this is the diffusion bonding, boron aluminum composite by diffusion bonding method. These are the aluminum foils between mat. Boron mat is placed. Bonding, their mat is, the fibers are generally bonded with acrylic adhesive, and layers of these fine foils are stacked with in between the mat, surface mat, and this laminate is pressed under heat at 500 degrees centigrade and 35 bar pressure, 35 MPa pressure in a die. Dies generally used are graphite dies. Liquid state means both will be in liquid. Particles are incorporated in molten metal. That is, matrix material will be molten. So this is the composite B4C MMCs. Squeeze casting, infiltration, and spray deposition. These are the methods. In situ methods means in situ process involves chemical reactions. It will be chemically reacted that result in the creation of reinforcing phase within a metal matrix. So reinforcing direction, orientation, and all will be created with chemical reaction. Then application of metal matrix composites are generally space, aircraft structures, boron aluminum tube to support the fuselage. Then mass decrease will be 145. In upper stages in space, even 1 kg reduction in mass also will give a lot of advantages of performance. Then this reduces the thermal insulation requirement because of very low thermal conductivity. And generally telescope, Hubble telescope, mast is used. Polymeric composites also are used as a mast. And military application, precision composites of missile guidance system depend very high dimensional accuracies are required here. That micro yield strength requirement is very, very high. That's very high micro yield stress required to create a plastic deformation or residual strain in very, very low. That is 1 into 10 raised to -6, you can imagine. So very low strain is required. That means dimensional stability is required. There we use MMCs. Then processing of ceramic matrix composites. Ceramic matrix composites are used when high strength, high hardness, high service temperature. Up to 1500 we can use. MMCs can be used up to 500. Polymerics also up to 500. MMCs can be used up to 500. And polymerics 350, 400, not more than that. Even polymer other resins also will go up to 400. Then ceramic matrix composite up to 1500 we can use. They are having low density, but the disadvantage is low, very low fracture toughness. So to increase the fracture toughness, impact load, catastrophic failure it will be. So to improve the fracture toughness, these ceramics have to be reinforced, such as SiC carbon. This will increase the fracture toughness because it causes the gradual failure. It is we have to convert this catastrophic failure mode to gradual failure mode by incorporating the reinforcements. The application where high mechanical properties retaining at extreme height service temperature, there we use ceramic composites. Just one typical method I am using, processing of CMC by hot pressing method. These are the fibers taken, impregnated in the slurry, matrix slurry. Here solvents and binders are also there in the slurry. Then they will be collected, they will be wound on a drum, and cut it at a in the tape form, and this stack of matrix impregnated fiber tapes that will become binder have to be removed. That is, binder is removed, burnout at 500 degree. Then again, it is pressed under very high pressure, and temperature is more than MMC. It is almost 1000 degrees temperature, and pressure of 7 to 14 MPa pressure has to apply. So this is the component. This is telling is very easy, but making ceramic composites is very costly affair because very high temperature furnaces are required, very high temperature sintering has to be done. So process will be very difficult and highly process oriented. In general, all the composite products are process oriented. Application of CMC is for high temperature applications where PMC and MMCs cannot be used, and very high, then CMC is used because of very low fracture toughness. We have to judge where it's appropriate application of only we have to use the CMC. Then high strength and high modulus and low density at very high temperature also properties will retain. So generally cutting edge inserts we are using in oxidizing and high temperature environment. CSIC, SIC, very high use in defense application we use. Silica for insulation purpose also we use. Carbon composites. Carbon composites use at very high, ultra high temperature. Up to 3300 degree centigrade we can use. These are very stronger and lighter than graphite. Carbon is brittle and flaw sensitive. So reinforcing of carbon matrix allows composite to fail gradually. There also fracture toughness will be very low. So we have to reinforce the carbon composites. This gives ability to withstand high temperature, low creep at high temperature, and very low density. They have a good strength and good tensile and compressive strength, high fatigue strength, and high alpha, high frictional coefficient. So brake discs are generally made. Processing of carbon composites made. Typical method of manufacturing of carbon composite is called low pressure carbonization. These are the various steps. Standard graphite phenolic prepreg we make, lay it up, cure in the mold, then pyrolysis start. This is pyrolysis means converting phenolic resin into graphite. Then step 3 is the resin impregnation. So that is this porous structure. This will be resulted in porous structure. So in this porous structure, we have to infiltrate the resin, impregnate the resin, and this process have to do 3 to 4 times to get the resin and to reduce the porosity and increase the slightly density. So the level of porosity is, some porosity will be there, level is to be reduced to acceptable level, and each time it will increase the modulus and strength. So 3-4 times we have to impregnate the component. Then ultimately we have to give the SiC coating, as these all carbon composites, they oxidize at around 450 degrees centigrade. So we have to give SiC coating and at outer layer. Then a very good use you can have. Sure. Then it is the sealing. I'm rushing through this presentation because I think time we have lost. Application of carbon nose cone. Space shuttle nose cone.
Madam, you can continue.
Degree. There we use carbon nose cone. Lowest weight of all ablative materials. This is listed. High thermal conductivity to prevent surface cracking. If thermal conductivity is low, insulation is more, means crack resistance will be less. So high specific heat to absorb large heat flux of re-entry heat flux. Large heat flux it will absorb. And high thermal shock resistance to low temperature in space, that is of minus 150 to 1700 degree due to re-entry. And carbon cone remains unchanged. It can be used in brake discs also. Application of carbon in brake disc. This is costlier than steel, but durability is 2 to 5 times more than steel, and very high specific heat, almost 2.5 times of the steel. Low braking distances, low braking times, that is 3.25 than beryllium. So large weight saving, almost large, as I told you, at upper stages, even 1 kg saving also will give very good performance improvement. So 450 kg on commercial aircraft, there is advantage you will get. Then mechanical fasteners also at very high temperature, carbon lose very low strength. I told, no, at very high strength, at very high temperature, mechanical strength retaining capacity is very good for carbon composite. Hence, high temperature fasteners generally use of carbon composites. These are the references in last 4 pages I have given, whatever is the presentation material. If any help is required, I have given email to coordinators. So please, all participants can contact coordinators and get the mail. I forgot to put here mail. So thank you. Thank you for patient listening. Thank you, ma'am.
Thank you, madam. Thank you, madam. See,
thank you, ma'am.
Beginners also can understand, madam. It's a very good lecture, madam. And you have covered a lot of varieties of composite materials, madam. Thank you so much. Madam,
I'm
can
sorry
we,
for the interruptions.
Madam, can this PPT be
Thank you.
provided for our participants, madam?
Send to your mail.
With your permission, can we share this PPT to our participants, madam?
So you can you can part with them. Yes, you can share. You can share.
Thank you, sir. Thank you. Because many participants are asking.
You can share, but in a notes form, I think you can share because a lot of number for clarity. I have put whole number of transparency. As such, understanding is slightly difficult. So I think notes like better. Share my mail if anybody is required. I can. But I forgot to put my mail address in this. Generally, we don't put in presentation. I am from defense side, so generally, we are very cautious. So I have not brought my laptop also. That is why. Okay, madam. Thank you.
Okay, madam. If you whatever format you provide, that we will share, madam.
Yes. Thank you, madam. Thank you very much. Thank you.
Madam, thank you so much. Participants, any questions? Please ask, madam. Dear participants, if you have any questions, please ask.
No, it's okay, madam. She has covered a lot, and I think it will be very useful for beginners for composite material subject. And I think if she accepts, it will be useful for our students, particularly for BE students.
Yes.
If she accepts the same material, if not 100%, at least majority of the points, I think we can.
Yeah.
We can have. Is it okay, madam? Yeah, please. Thank you so much for
Yes.
nice lecture. Yes, of course. Now on is yes, and thank you for accepting.
Yeah, lot of interruptions were there.
No. It is not. Sometimes it is not in our hand. It is a network problem here and there.
Thank you very much, madam. Can I?
Yes, please.